All right, so we're going to look at another multi-stage problem. So we're trying to utilize all of our knowledge from the whole semester. Or I guess that's the wrong way to say it. We're not going to use everything from the whole semester, but we need to be aware of all of that knowledge that we've gained over the course of the semester and be able to apply it appropriately within the context of a somewhat complex problem such as this one. Once we get into it, though, I hope you'll see it's really not that complicated of a problem. So let's go ahead and get started. So a bullet is shot into the block. The bullet rather is embedded into the block. The block swings up to a certain height, which is given right here. And based on this information, this height, we're supposed to find out how fast the bullet was going initially. And this is really quite an interesting problem because historically the gun manufacturers would use this technique to figure out what the muzzle velocity was. So that way they could improve their designs. It was a research and development tool, and then they could also use that for marketing purposes. And this technique was used for quite a long time until some more modern sensors and photography, high-speed photography methods became available. But in any case, we can replicate that, and we can look here during this collision. Certainly, we can say that's stage 1, and if it's a collision, then momentum is conserved. So we can use conservation of momentum, and we can say this is our initial, and then this is our final. So it's not two separate things hanging there. It's just, there should be a break there. So we've got V1I here, and we've got V2I, which is 0. The block was just hanging there. And we're trying to find out what V1I is. That's our main goal. That's our muzzle velocity. Okay. VF, we'll call it, is an unknown. And so if we were to apply the conservation of momentum principles here, we could say M1 V1I plus M2 V2I equals, and here we can just combine them, M1 plus M2, since it's a perfectly inelastic collision. But we have too many unknowns. That's an unknown, and that's an unknown, so we cannot solve that. We can look at the other part of what happened, which is essentially this block that's hanging from a string or rope or something swung, and so it's acting as a pendulum, and we know that we can very easily apply conservation of energy principles to a pendulum. And so I'm just going to change colors here to emphasize that this is a separate stage. Stage 2. And so initially, the bullet and block have some velocity, which we could call V sub I, and we don't know what that is. And then it swings up to some height, and we'll call that final. So the highest it possibly could swing up to, that means that the velocity is going to be 0, and HF is going to be 4.30 centimeters, or 0.043 meters. There's no springs involved in this, and so we can go ahead and apply our conservation of energy equation that just has 5 terms. There's no springs, so we'll leave those 2 terms out. There we are. When we think about, okay, let's analyze this. Let's say, oh look, there's already a dashed line there. That's kind of convenient. We can say that that dashed line is where the gravitational potential energy is 0. So, boom, that's 0. Kinetic energy final is 0. Because that's when it gets to its highest point, that's by definition when the speed of the object is 0. So it has no kinetic energy at that highest point. Of course, it's going to swing back, but we're not concerned about that. And then we've got work by non-conservative forces. So if we were to draw free body diagrams for this, which we'd have an infinite number of them, because there's the block at the lowest point, and then we could draw for every angle, and there's an infinite number of angles here. But at any point, if we're drawing our work diagram, at any point we're going to see that tension and displacement are perpendicular to each other. No matter how many of these we draw, the tension and the displacement are always perpendicular. Weight is a conservative force. The weight does work, but we don't care about that because we're only interested in the work by non-conservative forces, and we see that that's 0. So 1/2 mvi squared equals mgh. We can divide both sides by the mass, and we can say that vi is equal to the square root of 2gh. And we simply just are going to solve that. And that says 0.0430 meters, which came from here. And this gives us an initial velocity of 0.918 meters per second, so about 2 miles per hour. It was going 2 miles per hour after the bullet plowed into it. Not going to box that in. I'll just grab a circle on it because we're going to use this. It's going to become our initial velocity. I'm sorry, this initial velocity for stage 2 is our final velocity for stage 1. And so now if we know this value, now we only have one unknown in our equation, and we can go about solving this quite easily. Let me switch back to my other color here. 0.01 kilograms times V1I. This is going to be 0. And then we've got 3.01 kilograms times 0.918 meters per second. And we solve, do a little algebra. All we have to do is divide by 0.01 kilograms. Oops. And so therefore, V1I, we plug all those numbers into our calculator, we get 276 meters per second, which is approximately like 570, I don't know. But that's just a ballpark. But it's pretty fast, which is not unreasonable for the speed of a bullet coming out of a gun. So again, this is a two-stage problem. Momentum was conserved here. Energy is not conserved, not kinetic energy, not within the system. Some of the energy of this bullet, the 1/2 mv squared of this bullet, gets turned into heat and sound. And so we can't apply this equation. We don't know enough about applying this equation to think about how we would account for the heat and sound created. Somehow in this work term we could do it if we had a lot more information, which would be virtually impossible to gather that information. But we do know that momentum's conserved in this first part, and that's all we need to know. And if we go back, if you check on how much kinetic energy was in the system prior to the collision and how much kinetic energy is in the collision in the system after the collision, you'll see it's a lot less after the collision. But in the second part, energy is conserved, and it's quite simple to analyze this. There would be no reason to apply conservation of momentum here. It would actually sort of a difficult thing to apply conservation of momentum to for beginning students, because the other thing that's involved is there's an outside force pulling on it, so the net force on the system is not 0, and so we would have to really think about this from an impulse standpoint, and so that's more complicated. But doing conservation of energy on a pendulum, we've certainly done that before. That's no problem. And so we follow this through. And so this is a problem where we know more about what's happening at the end, and so we work backwards through the problem. But we did write this equation down first, and that's when we realized that we didn't have enough information. That's what sent us over to working on stage 2 first. All right. Hope that makes sense. If you have any questions, feel free to follow up with me.